And the interesting fluctuations associated to the dynamics, you only see if you consider trajectories. So that's the first message. Particular, what I'm just saying is that if one looks at static observables, this distribution of those observables is Gaussian, it's kind of boring. But if one looks at dynamic observables, and by that mean time-integrated observables, observables not of configurations but of trajectories, those have interesting fluctuations. They are non-Gaussian, and then typically they have fat tails. They have pronounced large deviations. So these large deviations are dynamical. They're not static. Static is boring. Dynamics is interesting, strongly correlated, fluctuating, and these fluctuations can only be seen if one considers statistics of dynamic observables, time-integrated observables. So therefore, what one needs is a statistical mechanics of trajectories to fully understand dynamics. Essentially, ensemble method, where the objects of interest are trajectories, rather than ensemble method for configurations. That's what we use in equilibrium stat mech. And that can be readily, be devised through the technology of large deviations. I'll say something about that. And this has been done for a problem of glasses. We did it about a decade ago with people in Berkeley. And one of the things that comes out is that with this one devises a method which is equivalent to thermodynamics and stat mech, but for dynamics for the trajectories of the dynamics. And one of the things that emerges is phase transitions in trajectories. Underlying this interesting structure, there are phase transitions in trajectories. One can see only those if one looks at ensembles of trajectories with these methods. And now these methods are, have found application, this trajectory phase transition, and lots of classical problems with interesting dynamics. So that's a starting point. So now, this is what I want to tell you about. So the question is, can one translate these ideas to quantum systems, in particular open quantum systems, non-equilibrium systems interacting with an environment? We started that program of work with my colleague Igor Lesanovsky about almost 10 years ago. So I'll review a bit of that because that's the starting point. And then I'll mention three things. The first one is also work with Madeleine, who's sitting somewhere there, and former students and postdocs in Nottingham. Connection between trajectories and matrix product states. That's the second statement I want to make because that's useful also to prove some of these pseudo-thermodynamics of trajectory statements I will make. And then some newer results because this is all about interesting fluctuations in the dynamics. The question is whether one can make rare fluctuations that are interesting typical. This relates to problems of control. And I will end up with statements about what's called level 2.5 of large deviations. People who know about large deviations know what I'm talking about. I'll explain for the rest later on. For quantum trajectory, I still published work also with Rob Jack of Cambridge. So, these are the kind of problems I want to discuss. Open quantum systems in the Markovian setting, where the evolution of the average state is determined by a quantum master equation of the Lindblad, etc. kind. So we've seen this in previous talks, including the talk just before the break. Hamiltonian, the coherent part, and jump operators that encode the action of the environment on the system, and that super operator often called the Lindbladian. But now associated to the evolution of the average state, which is deterministic, there is a quantum Markov process. And that is a process where the state evolves stochastically. And it can be, this equation can, in contrast to the classical Markov processes, can be unfolded in various ways. I'm going to call a quantum trajectory unfolded in terms of quantum jumps, the state, let's say it's pure, that evolves until there is a jump and an emission into the environment, evolves, emission into the environment, and so on and so forth. This evolution occurs over times that are distributed according to a survival probability controlled by the effective Hamiltonian, which is a Hamiltonian, and the other part of the Lindbladian that form what one can think of the escape rate operator for those jumps. The average state is the average of this fluctuating state over infinitely many trajectories. Okay? So just like in classical stochastic processes, there is deterministic evolution of the average state and stochastic evolution of the fluctuating state. And associated to these quantum trajectories, there are something I'm going to call, or some people call quantum jump trajectories, which is a classical trajectory of emissions. For example, one can see the emitted photons in the environment, and that's a classical record of, if you want, the measurement of the environment on the system. So we have quantum trajectories and quantum jump trajectories. So now, I want to focus on the properties of trajectories, of ensembles of trajectories. The dynamics generates trajectories with a certain probability. So the ensemble is the set of all dynamics that can occur, let's say up to time t, under probabilities. And that's the ensemble I want to consider, the set of trajectories of the dynamics. And to classify those ensembles, I want operators, I want order parameters, quantities that are functions of the trajectory, not just static quantities. For example, let's say the number of emissions, number of total jumps up to time t. That's a very simple trajectory observable. Each of these random trajectories has a certain number of emissions, and one can ask what's the probability to have a certain number of emissions. That I'm calling P of k. So now, at long times, and one can argue and prove this, these probabilities have, obey a large deviation principle. That's how it's called. They are the exponential of time, that's the quantity that controls the size of a trajectory, times a function of the observable, which is typically extensive in time, divided by t. And that function controls the structure of that probability at long times. It's called the large deviation rate function. Okay? But now the same information, modulo caveats, as the probability is contained in the moment generating function. I'm calling it set to start reminding you of partition sums. And that's the sum over all possible values of the observable, the probability of seeing that observable, e to the minus s, a conjugate field times k. The exponential, the average of the exponential of the observable with that field s up there. So this is the moment generating functions. Derivative of set gives us the moments of k. At long times, it also has a large deviation form. It's exponential in time, times a function theta of s that depends now on the conjugate field. K has been summed over. And that's sometimes called the scaled cumulant generating function, sometimes just the large deviation rate function. And these two functions are related by a Legendre transform. So if one knows this one obtains that one, modulo the convexity of Legendre transforms. So this is precisely the same structure as in equilibriums, the ensemble method of equilibrium.mech. So here we have something that's the partition sum, is a sum over all observables. It's exponential of the quantity controlling size, time in this case, volume in the classical case, times a function that's like a Helmholtz free energy. And the order parameter, if that's, say, the magnetic field, classically that would be the magnetization. The magnetization is also exponential, the probability in the volume, times the Gibbs free energy. So this is a structure, the large deviation structure of classical StatMech. We have here, but for trajectories. The observables are functions of the trajectory, extensive functions in time of the trajectories. So now, like in classical StatMech, one tries to calculate the partition sum, or rather the free energy. The derivatives of the free energy give you all the moment, all the cumulants, all the correlations. So that's what you like to calculate. Calculating partition sums is difficult. In the classical, in this dynamic case, there is a special direction, which is time. So you have a system evolving in time. Time is a special direction. The trajectories are generated by the dynamics I was describing before. And what that means is that this partition sum can be solved with a transfer matrix method, where the transfer matrix is a tilt of the Lindbladian superoperator. So you take the Lindbladian superoperator of a couple of slides before, that defines the dynamics, that generates the dynamics. You tilt it. The tilt depends on the field and depends on the field coupled to a certain observable. So the form of the tilt depends on what you're counting, the statistic of what you're trying to get. But then the largest eigenvalue of this tilted operator is that free energy for trajectories. So this reduces the problem from calculating a partition sum over trajectory to diagonalizing an operator. Still difficult, but slightly easier. Again, analogous to classical StatMech. So we have partition sum, we have free energy, we have a parameter that controls the large size, a conjugate field, and an observable. And this can be done for all kinds of trajectory observables, or collections of trajectory observables. You could be counting certain kinds of emissions and certain other kinds of emissions and doing the joint statistics and so on and so forth. So let's look at an example. Kind of very simple example of which we know essentially everything. So let's see whether this method tells us anything else about a problem of this kind. Let's say we have 3 levels, classical blinking setup, level 0, 1, and 2, some on resonance driving between 0 and 1, 1 between 0 and 2, but with a strength that's much weaker, and some decay from 1 to 0. Yeah, so we know what happens. If we look at the emissions, it's intermittent. The system's, loosely speaking, spends a lot of time they are emitting, every now and then gets shelved into and doesn't emit. So what's going on? So let's calculate now the statistics of the number of emissions of this simple problem. There is a Hamiltonian. There is a jump operator from there to there, therefore there is a Lindbladian. If I calculate the jumps, I tilt the Lindbladian. It's a 9 by 9 matrix, so Mathematica gives me the largest eigenvalue. Yeah. And I plot the largest eigenvalue. Remember, this is like a free energy. It's the black line there. Has to go through 0 at s equal to 0, because at s equal to 0 I'm tilting nothing. So it's essentially the largest eigenvalue of the original Lindbladian is 0 at s equal to 0, and has that shape. And notice that that shape looks like the one that the 2-level problem would have, which I haven't calculated, but that's what it would be. And then it bends out. And this is like a free energy. So let's go back to our StatMech textbook to see the relation between free energy and probabilities, or the log of the probabilities through the Legendre transform. So when the free energy is simple, it's just like a curve that goes through 0 like that one. When we do the Legendre transform, the probability is unimodal. It's essentially a Gaussian. Yeah. So if the free energy looks like that, we get a Gaussian, not very interesting fluctuations. But when the free energy bends, and in particular when it bends in the sense that there is one branch that crosses another branch, and you always have to choose the largest in this description, like in StatMech you choose the lowest, and you Legendre transform, what you get is that for each branch you would have got one node. That would be a probability of that branch, or the probability associated to that branch, but because they cross, there is a Maxwell construct. The Legendre transform gives you the complex envelope of the probability, and that complex envelope is a Maxwell construct. So when we have this crossing, we have a phase transition at that point, and that phase transition is associated with phase coexistence. First order, I'm drawing it for the first order case. You have one phase, let's say the liquid, another phase the vapor, and the coexistence at the phase transition. So now if we go back at this kind of pseudo-boring problem, we see that that bends, doesn't quite cross in a singular way, but bends a lot. So that's suggesting that there are two phases. And indeed, if one does the Legendre transform, the probability distribution is very broad. So in a sense, it reminds something like this, but smoothed out. And the derivatives of this free energy give us the values of the correlations, for example, of the order parameter, as a function of that field S, which is just the field I used to tilt, and which I'm using to study the statistics. So basically what S is doing, around S equal to 0, I'm looking at the statistics around the typical, at the top of the distribution. And as I tune S to one side or another, I'm focusing on the properties of the trajectories associated with different parts, the tails of the distribution. So that's what S is doing. It's allowing me to study the statistics. And sure enough, on one side, where the free energy looks like the 2-level, I have a large number of emissions. Typical trajectories are emitting all the time with a certain high rate. On the other side, where this flattens a lot away from the 2-level, the derivative is 0, and there are basically no emissions there. Typical dynamics occurs in the middle, and there are two phases, one associated with that branch and another one associated with that branch, that coexist in the middle. So what we have here is hallmark first-order transition physics, except that this is not a large system, so it cannot be a full transition, it has to be a crossover between an active phase and an inactive phase. So why do we see that? Because at coexistence, one sees both phases and sees sharp interface between the phases. These are bubbles in time, exactly like vapor bubbles you get in the liquid. You have two phases and a sharp interface between the two. It's exactly the same physics. So now, of course, this is a few body problem, and this is just a crossover. But this, in this simple problem, kind of opens up the, the intuition and the technology of StatMech for the dynamics. Of course, if you want a true phase transition, one has to go to a large number of degrees of freedom. I won't go into the detail, but for example, one can look at the transverse field Ising model under dissipation, for example, decay of, in local decay of the spins. So it's a system that's, can be scaled with system size. And in that case, again, the properties of the dynamics and the emissions, and now there is space and time as well, is associated with having two phases, one which is a polarized phase where there are very few emissions. This would be this one, and of large polarization, and an unpolarized phase, if you want, the ferromagnet and the paramagnet, where there are many, many emissions and a strong transition between them that can be crossed either as a function of physical control parameters, like the driving rate, the driving strength, or this counting control field, which what does is studies the properties of fluctuations away from typical behavior. So what I have tried to convince you up to now is that using this technology, trajectories generated by the dynamics, ensembles of trajectories, observables on those trajectories, and large deviation techniques to study the statistics of those observables, one can uncover these pseudo thermodynamic-like properties of ensembles of trajectories, or of the dynamics. And then think about dynamics in terms of things like this: phase transitions, different phases, coexistence, interfaces, etc. So let me discuss a little bit some of the interesting mathematical properties that, that are associated with this way of thinking. So first one is that ensemble of trajectories are matrix product states. This is just a way to classify ensembles of trajectories. So what's an ensemble? Ensemble is a set of objects with their probabilities. So the objects are trajectories, the dynamics gives them to you with a certain, the stochastic trajectory, the quantum trajectories, the dynamic gives them to you with certain probabilities, and one can collect all that information in a big vector that I'm calling a matrix product state, because it has the structure of a matrix product state. So I don't want, again, I'm trying to emphasize concepts more than actual details. So basically what one has is, given a trajectory is a state that has no jumps, then a jump, then no jumps, then a jump, and so on. So this sequence of operators tell you what the state is doing in the trajectory and what the probability or the amplitude in this case is for that particular evolution of the state. So if I use that amplitude and I associate it to a vector that indicates which particular trajectory it occurred, and I sum over all trajectories, which is with all numbers of possible jumps over all possible times between 0 and t, that's a matrix product state. It's a big vector that encodes all the information about the trajectories. And let me emphasize that this knows much more than the stationary state. This knows the stationary state and knows all time correlations are contained in this object. From this object, in principle, I can extract that. So as I'm saying that it's the ensemble, all the information about the trajectories generated by dynamics between time 0 and time t is contained in this big vector. So it's a big vector. Yeah, I'm calling it MPS for matrix product state. It's a continuous matrix product state, but never mind. At s equal to 0. This is what the original ensemble of trajectories is about. But when I count, I tilt. So when I'm counting, I'm trying to understand what's the ensemble of trajectories, not as the dynamics gives it to me, but reweighted by e to the minus s some observable, for example, the total number of emissions. So now I'm associating to each trajectory a weight e to the minus sk. It's related to tilting the operator, as I said before. And that gives rise to a different vector, and that's this matrix product state, which has essentially the same structure, except every time there is a jump, there is an e to the minus s factor, because this is the amplitude, is e to the minus s over 2. Okay, so I changed the vector. So this contains the original trajectories, this contains the original ensemble of trajectories, this contains an ensemble of trajectories where the probabilities have been tilted by that factor. This is like doing canonical, a canonical ensemble. Yeah? If I was doing, states, and that was the energy, and S was beta, the inverse temperature, I would take, the canonical ensemble would be e to the minus beta energy, reweighting just the probability of the states as they exist in the space where I live. So why is this useful? I won't go into details, but I'm trying to emphasize the analogy with the equilibrium stat mech that you know about, is that this is an ensemble associated with a certain value of S. S is the conjugate of my observable. I could have constructed an ensemble for a fixed value of my observable, just summing over all trajectories with a fixed number of emissions, not with reweighted by e to the minus sk and summed over all k, but a fixed number. And that would be a different vector. This is like the microcanonical, where you fix the observable, you fix the energy, yeah, instead of fixing the conjugate variable, fix the magnetization. Here we're fixing a trajectory variable. Well, it so happens that in the limit of long times, these two ensembles become essentially equivalent. There is ensemble equivalence. There is a version of the classical, in the classical case by Chetrit and Touchet, but this occurs in this quantum Markovian system, as long as the conjugate field, which sets the average in the canonical ensemble, is set to give you an average which is the same as the fixed value in the microcanonical ensemble. Exactly the same measured contraction that you get in the large volume limit between canonical and microcanonical. There are aspects of these ensembles which are not equivalent, but I won't go into that. This is essentially equivalence in the canonical and microcanonical case. So it's convenient to use this matrix product technology to formulate in a concise way these ideas. So we have these statistical mechanics of trajectories, and we can formulate the ensembles in a matrix product way. So let me try to say two more things, and then I'll be done, about 10 minutes. So first of all, what I've been doing here is using this field S to tune away from the typical behavior to rare behavior, to explore the full distribution. And this allows to uncover these different phases, for example, in these intermittent problems. So imagine you have a problem, for no reason whatsoever. Imagine you have like a chunk of a transverse Ising model that dissipates. This is real data taken from this model. And the typical behavior is that the emissions are not that frequent. So this is your probability distribution of emissions. Yeah, it's peaked there on the gray. It's not very large. You have those emissions. That's a typical quantum jump trajectory that you would see. But you know that further into, away into the tail, there are rare events, rare trajectories which are much more frequent. Yeah. So now, what I've been describing is methods to understand the properties of those. But imagine now that you would like to say, well, oh, that looks interesting. Can I engineer? Can I find the dynamics? That's a control problem. Can I find the dynamics most associated to the true dynamics that would generate that interesting process as the typical one? So then that one would become the typical one. And this would be the dynamics. So I'm saying this. Imagine you, in the previous cases, you find with this that certain rare fluctuations belong to a different phase than the one that you're seeing. And now you would like to engineer it so to see it to see it on demand, not to have to go and look for it in a very painful, statistically painful way. So using matrix product states, this can be proven. Finding the dynamics that would give this as typical, where originally was a fluctuation of another dynamics, is related to these vectors. That was my original dynamics. That's the tilted vector that describes this as a rare fluctuation of that. This as a rare fluctuation of that. So that's that describes an unphysical set of trajectories. Oops, something happened to my clock. So there we go. So this is an unphysical, so this vector has not been produced from a real generator. It took the old generator and tilted it by hand, saying, oh, I want to tilt it to see the large deviation properties of the original dynamics. But because it's a vector, it has a direction where its the vector itself wouldn't change. What would change is the basis in which I'm describing it, which in essence is what's the operator that generated it. So in the language of matrix processes, that's called a gauge transformation. The mathematics is something like this. So this is this tilted vector that's not physical. One can insert identities with a time-dependent operator G, and one can ask that time-independent operator G to make this vector into the ensemble of trajectories matrix product state of some other dynamic. So one can go from the original dynamics to the tilted, and from the tilted to a different dynamics for which this is the typical behavior. And this, in fact, is data for precisely this three-spin problem. So with this method, one can uncover interesting properties of the fluctuations, and then afterwards turn those, find the actual dynamics for which those fluctuations would be typical rather than rare. So I have like 12 minutes. More? Oh, I don't want more. So up to now, I hope to have convinced you partly that this is kind of, we really think is the right way to think about dynamics, stochastic dynamics, classical and quantum. Partly because it just opens the door of statistical mechanics that's been developed for 200 years for equilibrium. So let's go now to level 2.5. So up to now, I've been discussing level 1. That's the large deviation statistics of observables. That's called level 1 of large deviations. We heard the name Varadhan before. Level 2 is due to Donsker-Varadhan, which is something I'll describe in a second. Level 3 is the information about everything about the trajectory. It's very complicated. Everything you can extract out of trajectories is called level 3. So these levels is just how much can I explicitly say about fluctuations of some stochastic dynamics, in particular Markov processes. So let's go to classical Markov processes. So classical Markov process is, continuous time classical Markov process is something like this. I'm in a configuration X. At some time I jump to configuration X1, X0, X1, then at some other time to X2 and X3 and so on and so forth. There's a classical Markov chain. And there are two quantities. One is how much you survive. This thing given e to the minus ith effective in the quantum case, essentially. In the classical, it's just an escape rate from a configuration, and the rate to jump from one configuration to another, which I will call W. So now, if I have a very long trajectory, and by ergodicity from long trajectories, I can infer information about an ensemble of trajectories. So if I have a long trajectory, there are two interesting quantities. One is called the empirical measure. So that's from the residence times, I can estimate what is in the long time, in the stationary state, or in a very long trajectory, which may or may not be typical, the measure of occupying the state. I'm calling that mu of x. That's the probability of being in state x, and I get it from a long trajectory from the residence time. So if you give me a very long trajectory, I can just do the histogram of the residence times, and I get this empirical measure. Eventually, this empirical measure is a fluctuating quantity that will converge to the stationary state measure, but it has fluctuations. So it's a trajectory observable. It's a whole vector that fluctuates. It's called empirical measure. And similarly, there are empirical fluxes, counting how many jumps between any two pair of states there are on a given trajectory. So it's a matrix Q, X, Y. So it's a function of trajectory, so it also fluctuates, and in the long time limit is related to the typical rate to jump between states. So what's level 2.5? This is kind of revolutionary results in large deviations in the last 5 years or so. So level 2.5 is an explicit form for the probabilities of the empirical measure and the flux. These are very big objects. These are probability in a trajectory. I populate the states with that probability, with that vector, and I jump between two pairs of states with that matrix. So this is a very, very big object. And it's called 2.5 because it's much, much information on the level 2 I was talking about, a single observable. So by large deviations principle, it's exponential of time times a rate function that's explicit, and this is kind of the surprising result. It has a very simple form. So for all classical Markov chains, that's the form of that probability distribution. So it's explicit. It was a big surprise. Conjecture first, or postulate, or taken out of the air and correctly by Maes et al., and then proved mathematically, so physics trailing maths again, or the other way around. So it's explicit. And the other thing is that it's complete, in the sense that if I know that, I can know the statistics of any level 1 of any observable, and in particular level 2 is just the statistics of that object. I can get the statistics of anything by minimizing this guy. So this guy has the empirical measure, the empirical distribution, and empirical fluxes between states, the probabilities of those trajectories. The statistics of any observable is minimizing this rate function over all mu's and q's, such that over those mu's and q's, one gets the value of the observable k. That's called contraction. So what I have is the full information about all of the statistics in this level 2.5. So now, up to now, I've been essentially translating all the classical into this quantum Markovian. So I just will flash some results without proofs. But what I'm going to tell you is that one can devise an equivalent level 2.5 for quantum trajectories. So I'll show you the result. I'll try to explain how I got there, and then I'll be done. So how do we get this? So in the classical case, x is a state, is a configuration, and in a trajectory it jumps from one to another. So that will become now the fluctuating state. I'm calling it psi. And the fluctuating state obeys what we tend to call the Belapkin equation for our late Nottingham colleague Slava Belapkin. Yeah, so it's a stochastic differential, quantum stochastic differential equation for the state. So psi of t evolves with this equation that has this nonlinear form because it preserves the norm of psi and involves the effective Hamiltonian and the jumps. And I wrote it for one jump, but the form is essentially the same for more jumps. So now, the expectation value over the state becomes the density matrix that evolves with the Lindbladian. This is one curiosity. If I have an arbitrary classical Markov process and I write the equation of motion for the expectation value, it's not closed on the expectation value. In the quantum case, the expectation value of the fluctuating state gives me an equation that's closed and linear, and that's the Lindblad, the Lindblad, etc. master equation. So now, but in the classical case, I also have a deterministic equation for the probability of the fluctuating state. Yeah, Fokker-Planck equation or classical master equation. So what we need is a equation for the probability of the fluctuating state psi, kind of a Fokker-Planck equation for psi, that's a quantum state, and well, here it's written. And it has a form associated with the jumps, and it has a part associated with the no jump evolution. So this is the Fokker-Planck equation. This is essentially figuring out how to make this dictionary translate one thing to another. And if we have a fluctuating state evolving like that, we can define an empirical measure and a flux. So what's the empirical measure is what's the probability that the state, so it's basically a delta function of the state at time t being what's the entry of this vector mu summed over all times. I'm not dividing by all, I'm not dividing by time just to make it concise, but it's basically what it says here. If psi is a random trajectory, is a stochastic trajectory, what this extracts is with the histogram in that trajectory of residence in states psi. Okay? And similarly, there is a flux. And what's the flux doing? It's doing the same, but for jumps between psi and psi prime. So in the classical case, one jumps over basis states, over classical configurations. Here, one in principle jumps between any two possible states in the state space of the system. So this is integrating over all times. The state just before was psi, and after a jump, the state just after is psi prime. and this gives me the fluxes. So this definition translates immediately, and I give you the answer. So this is level 2.5 for quantum trajectories. So the probability of finding a flux, an empirical and a flux set of empirical vector flux matrix Q in trajectories up to time t is given by this large deviation form with this rate function I 2.5 that has a shape that is not too different from the classical one. In the sense, in the classical case, details don't matter, but in the classical case it is Q log Q over something with the empirical minus 1 times the empirical there. The shape is essentially the same, except that now there is a continuity equation. And the continuity equation is that the divergence of the flux, how much goes into a state and goes out from a state, the difference of that has to be compensated by changes in the empirical. This is a continuity equation for probability, or for the state, in the space of states. So this is a level 2.5, and this is the answer. So you say, so what? I would say, I think it's pretty interesting how all these classical ideas can be translated to the quantum. But this is useful. It's not just interesting, but it's useful for two reasons. If I go back here, this statement, two things I'm going to say. This statement is a control statement in the following sense, and people like Chetrit and Touchet have formulated these ideas in the classical case in the language of control, in the sense that finding the probability through the rate function for some observable in this way is equivalent to finding a dynamics that gives that observable as that value of the observable as the typical. So it's going from the normal dynamics and finding the other dynamics. And this is a control problem. It's related to me maximizing something, very much in the reinforcement learning spirit. And then the other thing is that if we have a variational method, because we're saying we have to minimize to get the probability, the rate functions, we can obtain bounds in the following sense, that if we want that, we have to do that minimization. That's usually very hard, but we know that if we get anything that satisfies the continuity equation, it will be an upper bound to that, and therefore an upper bound to that. So this allows to relate something that's difficult to something that usually it's easy. And this is true for any trajectory observable. So this is the correct way to do variational theory on dynamics. And this is an example. So one can think of a simple dynamics which has renewal, have many renewals where the state goes into one state, or there are many jumps that take you to specific states. And one could try to calculate the rate function for the, say, number of emissions. That's away from the typical. That's the typical, alpha away from the typical. And one can use an answer and say, well, maybe these dynamics, I don't know, it's just the original dynamics where I rescale time by alpha t. That's probably not correct, but this can be done. So if one plugs it, one gets immediately a bound. That's interesting because it's a Kullback-Leibler divergence between the original probability for jumping, jumping again at time t, with the probability where time has been shifted by at, and we can discuss that. And what those bounds are if that's the true probability, those bounds are always, so the rate function is minus is minus this one. So those bounds are like the dotted line. They are bounds that say that the fluctuations of the true process are always larger than those of the bounds. So fluctuations are always bounded from below. So fluctuations are always larger than the ones of the bounds. And this relates to something that's there's a lot of activity in StatMech nowadays that are called thermodynamic uncertainty relations. This is the right way to generalize these thermodynamic uncertainty relations, fundamental relations for precision that have a thermodynamic origin, the statistical mechanics origin, to the quantum setting. I think I ran out of time, and I'll stop there.
Thank you. So we have time for questions. Yeah, Adolfo, yeah. Need this or?
Maybe two quick questions. In the first part of the talk, do you have an analog of second-order phase transitions between ensembles of trajectories?
Yes, yes. All of these things exist. So that would be a situation where these two branches, where the two branches meet with the same derivative. Yes, these are, for example, in a problem like this one, this is a first order transition, and in many situations, these end at a critical point. And at the critical point, what you would have is a continuous phase transition, and it's a second order. So these exist.
And this is, in principle, something you could drive dynamically from one phase to the other one?
Well, so if it occurs at S non-zero, as is often the case, then it's a second order phase transition, the nature of fluctuations. So it means that if the system fluctuates a lot, it changes phase to achieve a large fluctuation, lots of emissions or a particular large current or something. And in that case, you can drive it in the way I described with this so-called gauge-dupe transformation to be of that kind. I think first-order transitions are more interesting, but both exist. The whole, slew of things you have in thermodynamics, you have here.
Maybe quick one about the last part. Is it related to Fisher information? This level 2.5 looks like a relative entropy between fluxes.
No, well, it is
at different times.
It is a relative entropy. That's essentially how you derive it. So we can talk about that. Yeah.
Are there more questions? Yep.
So on the more technical level, so you need to have ergodicity. So this is like a Markov process on the space of states. Mm-hmm. So for this large deviation results, do you need the ergodicity of the Markov process, or?
In principle, yes. So one can generalize it, but usually things are simpler if it's ergodic and it's irreducible, and whatever phase transition you have in some limit. Mm-hmm. So it can become irreducible in the limit of the phase transition. Yeah.
So because it only recently has been proved, under some condition that this process is ergodic. So you need to have some. Well, it's not clear if generic processes are ergodic, but under some purification condition they are ergodic.
Oh, you mean the quantum process?
Yeah.
Yeah, it's true. Here we're assuming that.
Yes.
In that result. So how broad this result is, I'm not so sure. Okay.
It's recent. Yeah.
Okay.
More questions? No, so if not, let's thank Juan again.